This is the 24th lecture of the course MTH 204A for section B. Recall that in the last lectures, in fact in the last two lectures we were talking about examples of rings, and in those examples we have seen that there are several rings which are indeed contained in some other bigger rings as subrings. So, in this lecture first I will talk about an important subring of any ring. So, let R be a ring. So, again let me remind you that we always assume a ring is always having a multiplicative identity, but not necessarily commutative. So, we start with any ring R, then we define the center of the ring R. So, this is exactly defined in the exactly similar way to that of center of a group. So, here we collect all the elements of the ring which do commute with respect to multiplication with all other elements in the ring. Remember, I mean for addition it say in R, since R plus is an abelian group. So, with respect to addition, if we look at the center of the abelian additive group, then that becomes whole R. So, it is not at all interesting. And I mean so therefore, whenever we say center of a ring, we always mean the center with respect to this multiplication, and it is easy to see that this center is whole. So, I leave it as an exercise. Center is R itself, if and only if R is commutative. Okay. All right. So, this for any ring R. So, you can easily see that the ZR is a subring of okay. All right. Now, let us talk about ideals. So, recall that in case of vector spaces in the situation of vector spaces, if we take any subspace, then we talk about the quotient of the vector space modulo that subspace, and that indeed gives us a vector space smaller in some sense. Similarly, for groups we have subgroups, but of course we cannot consider the quotient with respect to any subgroup because because there will be problems. So, there is a very special kind of subgroups, namely the normal subgroups, with respect to which we can consider the factor groups. So, I mean from these two things it might be quite tempting to guess that in case of ring we should be able, in case of ring what we should expect is that we should be able to talk about the quotient of a ring with respect to any subring, or if not all subrings, then some special kinds of subrings. But unfortunately here it is not true. So, you will understand what is actually going on. So, let me try to explain why it is not actually true, because by definition a subring contains the multiplicative identity. So, I mean as an independent observation we should see that suppose in a ring if 1 equals to 0, then that immediately implies that for any A in R, A times 1 is A has to be 0. So, therefore, if this is the case, then ring will be trivial ring only. So, certainly it is not be of it is not going to be of any interest to us. Okay. So, now the problem with considering the quotient of a ring with respect to a subring is the following, that once you do that, then basically this R prime consists R prime, and suppose this is defined, hypothetically try to speaking, suppose this is defined, then the unity of R is also contained inside R prime, therefore in the quotient it is going to be 0. So, now the unit, so in this quotient ring we see that the unity is 0. So, therefore, it is actually like this is actually pointless, right. So, therefore, unlike the situations, unlike the case of vector spaces or groups, here we cannot talk about the quotient of a ring with respect to a subring. So, here in order to talk about quotients we have to consider other kinds of objects. So, at least what we are convinced now by this is the the special subsets that we must pick up, that we must consider, I mean it is to be considered in such a way that one cannot be contained in that, because if one is contained, then this is going to be utterly a pointless one. So, the special subsets that we are going to choose, first of all they must avoid 1. Okay. So, now let me define ideals. So, ideal is ideal is the desired kind of subsets of a ring with respect to which we can talk about quotients. So, let me define. So, a subset of R is said to be an ideal, if the following happens, that first of all it is a additive subgroup. So, let me put it in this way: I plus is a subgroup of the additive group R plus, and then the most important concept is for every x in I and A in R, Ax belongs to I. Okay. If this is the situation, then we will call I to be an ideal. Okay. So, before I should so this is the definition of ideal. Now, I should go for talk about some examples, so that you will be able to understand the definition. But before I get into the example, let me put a remark that if R is not commutative, then for any x in A and A in R, x in I and A in R, there is no guarantee that Ax and Xa will be same. There is no guarantee. Okay. So, these two things are different. So, in view of this, I mean usually what we do is we call, if an idea a subset where this is happening, that is like if I take any x in I and then we multiply it by any element from the ring from the left, then if it is contained inside I, then we will call such ideals more more specifically as the left ideals. And if this condition is replaced by so x A in I, then we will say I to be a right ideal. Okay. So, if the with the group element A, with if we are multiplying x from the right by A, then we call I to be a right ideal. And if it so happens that for any x and A, both Ax and Xa though may not be different, but still both of them lies in I, then we will call I to be a both sided ideal. Okay. So, so left ideal means, so the definition that we have first given is actually the definition of left ideal. Similarly, you can define right ideal and then both side ideal. So, this division is somewhat meaningful if the ring is not commutative, but however you can see the ring is commutative, then any left ideal will be automatically right ideal, in fact a both sided ideal. So, as I said that more often than not, the ring in this course, the rings that we are going to encounter are commutative rings. So, therefore, we do not have to bother about whether the ideals that we are considering, they are the ideals are left ideals or right ideals or both sided ideals, we do not have to bother about. Okay. And also one thing that of course, we will be developing the theory in general, theory in the generality in this course. So, therefore, it is not the case that every time we will assume the given ring to be commutative. So, whatever we will be proving, whatever we will be we are going to establish, we will prove theorems, we will prove results for left ideals only, and of course, from that you can see that one can also develop its analog, appropriate analogs for right ideals as well. Okay. So, therefore, in this course, unless otherwise said we always consider left ideals, but again when the R is commutative then it does not matter. Anyway, so yeah, so this is the definition of ideal. Now I should talk about examples, then you will be able to understand what this actually means. So first let me take a very simple ring, namely Z. So for any n in Z, in fact nz is an ideal. That is quite easy to see. Okay, it satisfies all the properties. In fact, in this case you see that these are all the ideals. Why? That is precisely because that this if I is an ideal of Z, then I plus has to be a subgroup of Z plus. Now we have a complete classifications of all subgroups of Z plus, namely these are of the form n times Z. So therefore if I is an ideal, I has to be of that form. Okay, and then since these three objects are already ideals, so from that we immediately conclude that from that we immediately obtain all the ideals of Z. Okay, so thus we have all the ideals of Z. It's also whenever we are doing something for Z, it's also worth looking the same for in the polynomial rings. So the reason you will understand soon. So let F be a field, and so okay, by a field what I mean is it's a ring, a commutative ring, and every non-zero element is having an inverse. Okay, so it's a special kind of ring. That's the definition of fields. And if you but yet if you are not comfortable with general fields, you can consider F to be Q, R, or C, or Z modulo PZ. So if F is a field and X is, and if we consider the polynomial ring in the single variable X, so I mean we will see that very soon that the Z and Fx, they do have many things in common. In fact, both of them are the I would say the prototypes of something called Euclidean domains, but I will get into that later on. So right now what I am doing is that the way we have found out all the ideals of Z, we ask the same question for Fx. So Fx is a ring. What are all the ideals of the Fx? Okay. So a lot of things are going to be same. So first of all, we can immediately see that if F is a polynomial, if we consider a polynomial in Fx, then consider all the multiples of all the multiples of F by polynomials. It's easy to see that this is also an ideal of Fx. So it's exactly like this, that if we start with an n and then we keep on multiplying by elements from Z, then we will get an ideal. Exactly the same thing also happening here. And now the important part is we are going to show that every ideal of this is going to be of this form. So thus like Z, we obtain all the ideals of this of Fx. So how to find all the ideals of Fx? That's basically a usual division algorithm, which I presume that you have you are familiar with. So let I be an ideal. I be an ideal of Fx. So if I is, recall that how we obtain that every ideal is of the every additive subgroup of Z is of this form n times Z. So the same kind of argument will will be applied here. So if the ideal is the trivial ideal, then we don't have anything to prove. If it is not trivial, then there exists a non-zero polynomial in F. Okay, so hence it makes sense to talk about n. So let me put it m. Maybe I should say greater or equal to 0 such that there exists f in I with degree of f equal to. So, what I am doing is corresponding to every polynomial in I am collecting its degree. Okay. Corresponding to every polynomial I am collecting its degree, and therefore, this is the collection of all possible degrees of elements lying inside I. So, this is a non-empty subset of non-negative integers, non-empty because here we have assumed that I is, in this case we have assumed I is non-trivial. So, this is a non-empty subset of non-negative integers, hence by well ordering principle it will admit a minimum. Let us call this minimum as n, and minimum means indeed there is a, there is a polynomial, let us say f naught in I such that degree of f naught is n. Now, so you see this exactly same kind of argument all we applied when we showed that every additive subgroup of Z is of the form nz. So, we take the least positive integer, least non-negative integer, So, there we have to take positive integer because 0 was anywhere inside that. So, least positive integer lying in that subgroup, and then we proved that every other element in the subgroup is a multiple of that. So, that is exactly we are going to do here. We are supposed to show, now we are going to show that like this ideal, like I is nothing but, I is basically the ideal consists of all multiples of f naught. So, how to show that? So, things are exactly done in the exact similar manner. So, simply that let G belongs to I. Okay. Now, we are working with, so we can divide, we can apply the division algorithm, because whenever we are given to polynomials at least with coefficients from a field, then we can talk about the division, then that yields a quotient and a remainder. Okay. So, that is exactly what we are doing here. So, write f z as f naught h plus some r, where where there are two possibilities, either r is 0 or degree of r. If r is non-zero, then degree of r is strictly less than degree of f naught, which is n. Okay. Now, you see that this implies G minus f naught h equal to r. Okay. So, G is in I, f naught is in I, any multiple of f naught will also be in I, therefore, the left hand side lies in I, that shows the right hand side will also lie in I. But what about the right hand side? The right hand side, it is a, if this possibility happens, that is r is non-zero, then if this is the case, then this shows that the I, inside I, this r is a non-zero polynomial whose degree is less than that of, whose degree is less than that of n, less than n. Okay, here I should remove 0, because usually the degree is not defined for a 0 polynomial. So, and that is a contradiction, right, because n is the minimum one. So, therefore, thus like proceeding in the exactly similar way to that of the case of Z, we obtain all the ideals of the polynomial ring over any field. Okay. Now, the natural question at this point is, if we replace a field by any ring, then whether this happens? No, that is not exactly true. We will see examples. Okay. That is not exactly true. In fact, like you can also see that if we we will see. The way we can see is, if we take R to be, let us say some polynomial ring with a different variable, then in a different variable, then this is going to be a polynomial ring maybe over a field in 2 variables, and then we can immediately find out an ideal which is not the multiple. Well, let me rather tell you, but I won't justify here. So, consider R to be let us say Rx, and maybe I should write it y. So, therefore, this is nothing but Rx y. We will prove soon that this is nothing but isomorphic to Rxy, and inside Rxy, if we consider the ideal generated by, well, I will define its meaning. So, the ideal generated by x and y, then it is easy to see that this is not going to be principal. I will define the meaning of ideal generated by a subset in a moment. Okay, so, but the main point is that if we replace Rf by any field, then certainly it is not true. Okay, now let me make the definitions. So, both in I mean what we observed in case of in case of this polynomial ring and Z, that if we start with an element and then considers all multiples by elements from the ring, that is going to be an ideal. So, this is something you can immediately realize that this is something that holds in the generality. So, given any ring R and A in the ring A, so the collection of all elements of this form, it is easy to see that this is an ideal of R, So, this is what we denote by this. Yeah, so I think I should change them here. So, this do not confuse that with ordered pair. I mean, again I will explain the convention. So, this is called the principal ideal generated by the element A. Okay. So, thus what we have proved is both in case of Z and in case of the polynomial ring over any field, all the ideals are principal ideals. Okay. Well, now I should now I would like to now tell you the meaning of ideal generated by a given subset. Okay. So, as usual, let R be any ring, S be a subset of R, of course non-empty, because for empty you can immediately, you know what to do. So, you want to talk about a ring, an ideal generated by the S, that means an ideal that will contain S, and this is going to be the smallest ideal containing S. Like earlier we have seen smallest the subspace generated by a set S was the smallest subspace, smallest means in the sense of containment of the vector space, and also we have seen the subgroup generated by a subset, right. So, similar things we are going to define here. So, the thing is we sometimes use these notations or other authors use other notations. So, let me directly write down what it is. So, I mean let us try to observe, let us try to see that given S, if you want to talk about an ideal containing S, then what are the elements that should be there in that ideal. So, first of all, like if I consider any element, let us say x from S, then in that ideal any element of any multiple of x should be there. Okay. Now, if we take another element y, then also its any multiple has to be there, and since this additive subgroup, so its sum has to be there. Now, why for 2? If I take 3 elements x1, x2, x3, then any multiple of x1, any multiple of y1 and any multiple of z1, any multiple of x3, and their sum must be there. Okay. So, that is how we can see that it consists of all elements of this form Ri, Ai, I from 1 up to n, where each Ri is in R, A1 up to n in S, and n must be an integer. Okay. This is exactly same as the definition is same as the subspace generated by a subset. So, exactly the definition is the same. So, in particular when S is singleton, then this will contain all the multiples of that generating element. So, therefore, you see that principals ideals are special cases of this. So, this is called the ideal generated by S. and it is not quite, it is actually quite easy to see that this is going to be the intersection of all ideals containing S. In the exactly similar manner to previous situations, and in fact if we consider any ideal containing S, then that ideal must contain this ideal inside as well, okay, because whenever these elements are there, then any multiple will be in that ideal, so the sum will be there. And one more thing, that here n is not fixed. So basically what I mean is that I mean, if we take for any natural number, if we take n elements, a1 up to n, and then all the such combinations will be there, okay. All right. So here what we let me again at least when S consists of exactly 2 elements, let me explicitly show you what that ideal is going to be, then you will be able to understand what it means. So suppose X is, let us say, 2 elements A and B. So then what is going to be the ideal generated by S? First of all multiples of A will be there and all multiples of B will be there. Now any multiple of A and any multiple of B, if we take their sum, that has to be there, and these are all. So therefore this is exactly RA plus SB, where R and S belonging to R, okay. So like when S was singleton, then we see it is exactly principal ideal. When X is just consists of 2 elements, then the ideal is consists of all elements of this form, and then you can extend it to any finite set A1 up to An. So therefore this will consist of all elements which are the combinations of those AIs with coefficients from the ring, okay. All right. So thus we have defined what we mean by ideal generated by subsets. Now let me talk about some more examples of ideals. Okay, so one thing I mentioned I forgot to mention is the difference between ideal and subring. So as I said that in the beginning that unlike groups or vector spaces, we cannot think of quotients of rings by subrings, because subrings contains the identity, okay. Subrings contain the multiplicative identity, therefore we need to talk about some other thing, some other object, namely ideals, with which we will be able to talk about quotients. Very soon we will see that, but here the difference is that try to understand that suppose we have suppose I is an ideal. Suppose I is an ideal, the question, can it be a subring? Can an ideal be a subring? That is exactly, so if it is a subring, then 1 will be inside I, identity, okay, 1 will be there, and if 1 is there, that implies for every A in R, A times identity, which is of course A, will be inside I. So therefore if 1 is there, it forces I has to be whole of R, okay. But of course for any given ring, the trivial one and R itself, these will be ideals, but these are the perhaps two extreme cases. So and these will be perhaps extreme cases, and what we have just shown is that an ideal cannot be a subring unless it is whole of R, okay. So this is the difference between ideal and subring, that ideals are different from subrings. So in fact if an ideal contains 1, then it cannot be proper, okay. Okay, so let me now talk about some more examples of ideals. So the following is a very important example that is used in the construction of real numbers from that of Q by the method of Cantor. So we consider all rational Cauchy sequences. We consider all rational Cauchy sequences. So each an, so it's a sequence of rational n numbers, and the sequence is Cauchy. Okay. So, we consider all the collection of all rational Cauchy sequences, and it is easy to see that this is a ring, this forms a ring, because the addition of two rational sequences will be rational, and since both are Cauchy, the sum will be Cauchy, and yeah, so this is going to, it is easy to see that it is a ring, and here the multiplication is the term is multiplication of sequences. Now, inside that we consider the following ideal that, so if this is my R, so consider the ideal of all null sequences. Here null means it goes to 0, the limit is 0, okay, 0. So, this is my I, and as expected I will verify this to, I am leaving this to you to verify. This I is an ideal, I is an ideal of R. Okay. Similarly, like we can also see the ideal of all null sequences in the ring of all convergent real or complex sequences. So, let me simply write down that the verification of this, to verify this you need some elementary analysis, which I am sure you are equipped with. So, in this case now my R is going to be the all rational sequences, not rational sequence, maybe any real sequence or complex sequence. Maybe I should do it for real here. Okay. The same goes for complex as well. So, then more importantly this is convergent, Okay. So, it is easy to see that it forms a ring, and then inside that we do have such sequences such that you can immediately verify like this that it forms an ideal. Okay. Next examples of ideals we will see, we are going to talk about is in the space of functions and continuous functions. So, consider any metric space, or if you are comfortable with it, you can consider any general topological space, and well, for simplicity let us take here only metric space. Then we talk about all continuous functions from x to R or C. For simplicity let us take R. There is no harm if we replace R by C. So, this is, we have already convinced that this is a ring, and inside this ring we can talk about, so fix some x naught, in x. Now, consider all the collections, all the continuous functions which vanish at x naught. Okay. Maybe you can denote the m x naught, or maybe some other textbooks use this notation I x naught or something. That is not the main point. We are considering all continuous functions vanishing at that point, at that given fixed point. Then it is easy to see that it is ideal. Of course, you can immediately generalize that, in the sense that you see that just fixing one single point, it is not actually going, it is not actually giving you something very special. So, what I mean by this is, if instead of just a fixed point, just a point, if we just fix a subset of x, any subset, finite or infinite, then if we consider all functions, continuous functions, in x, this also forms an ideal, because if we take any two functions from that, the sum is going to lie there. Similarly, if I take any function from the function vanishing at every point of S and then multiply that by any function, any other continuous function, the product will again vanish at every point of S. So, it is I mean immediately without even getting into computations, you can immediately verify. Okay. So, we have seen now let us talk about ideals of fields. So, as I said that what are the prototypes of a field is Q, R or C or Z modulo P Z. By a field in general we mean it is a commutative ring where all the non-zero entries are units, that is having inverses with respect to the multiplication. It is a commutative ring. Okay. So, if R is a field, what are the given F a field, what are the ideals of F? Okay. So, of course, we see that we have these two extreme cases. Now, if we take any general ideal not equal non-trivial ideal, so what does that mean? That there exists x inside I, okay, which is non-zero, and then since it is a field we have x inverse. Okay. So, by the definition of an ideal, x inverse times x also lie in ideal. So, this is 1. So, therefore, the ideal contains unity, and as I have already seen that if an ideal contains unity, then it has to be whole F. So, then this forces I to be whole F. Okay. Again, let me tell you what I have done. What we have actually proved is if F is a field, then every non-zero ideal is going to be the other extreme one, that is whole F. So, therefore, a field has only two ideals. Okay. In case of fields, we do maintain a convention that we assume 1 to be not equal to 0, because if even for a general ring if 1 is 0, then the ring has to be trivial, but certainly like in that case there is no point of talking about a field, because there is no, like the way fields differ from a general ring is there you can talk about inverses of non-zero elements, but if it is trivial then certainly there is no non-zero element. So, we discussed such I mean uninteresting, we discussed such bogus cases. So, whenever we talk about fields, we will of course keep this convention into the picture. Okay. So, that is what we have proved, that a field has only two ideals. Okay. Now, let me ask the converse question, that suppose a ring, let R be a ring, let R be a ring that has exactly two ideals, then does that imply R is a field? Okay. This is the question we are now dealing with. So, first observe that whenever I say exactly two ideals, then certainly R cannot be the trivial ring, because trivial ring has only one ideal. So, I am saying that exactly two, well I should, if you want two distinct, I should say in that case exactly two distinct ideals, then this forces R has to be non-trivial, and since any given ring R, we know that we do have at least two different, in any non-trivial ring R we do have at least two different ideals. So, therefore, whenever we are given this, from that you can immediately say that these are all the ideals of that ring. Okay. Now, we are going to see whether this is a field or not. So, let us consider any non-zero element. So, since we are inside a ring, we can talk about the principal ideal generated by this non-zero element A. So, this ideal, this is going to be an ideal, right? In any general ring, the principal ideal is an ideal. Since A is non-zero, so this ideal cannot be the trivial ideal. So, therefore, it has to be whole of R. So, what does that mean? There is a multiple of A which is identity, and that shows that that shows that you are okay. So I think it's better to, maybe I can say, a commutative ring. Yeah. If in a commutative ring we have exactly two distinct ideals, then that forces are to be, so that provides an affirmative answer to this question. Because if you take any non-zero element, then the principal element generated by A will be whole of R, therefore that forces A has an inverse. Okay. All right. So thus this shows that a commutative ring is a field if and only if it has exactly two distinct ideals. Okay. Now we will talk about operations on ideals. So it's exactly same as operations on vector on subspaces or vector spaces or subgroups. Namely, we are going to talk about sum of ideals, intersection, product, all these. So let me do that. So these are very small observations, hence I should leave that to you to verify. So suppose we are given let's take a finite collection to make things simple. Suppose we are given these n ideals of a ring R, not assumed to be commutative. So in that case, it's easy to see that their sum. So what do you mean by their sum? Is very naturally defined. The way the sum is defined for subspaces, namely it is the sum of all elements of this form. Okay. So this is what we call it sum. Then it's easy to see that if these are ideals, then their sum is going to be an ideal. Okay. And of course this operation, operation addition on ideals is associative. So what I mean by this is, suppose, so this is observation 1, this is observation 1. So if A, B and C are ideals in so as I have already told you that in the results that we are going to prove, the general results that we are going to prove, unless otherwise said, all the ideals are assumed to be left ideals. You can immediately convince yourself that analogous results can be formulated and established for right ideals as well. But of course, when the ring is commutative, then you do not have to bother about anything. Are ideals of R, then A plus B plus C is same as A plus B plus C. Okay. And that is exactly same as A plus B plus C. Okay. That is easy to see, that shows the operation, this addition of ideals is associative. Now let me talk about product of ideals. This is somewhat non-trivial. So product of ideals. Product of ideals. So let me first let me first talk about the product of just two ideals, and once you understand that, we can generalize that for any finite collection. So suppose we are given two ideals, again ideal means tacitly all the ideals are assumed to be left ideals, ideals of R. So we want to talk about their product which we want to be an ideal. So at the very first sight, it is very tempting to write down that we will define this ij as this, like the product of two subgroups of a group. So it's very tempting to write like this, it's very tempting to define the product like this. In case of groups, indeed, like of course not always it is going to be a group. If something is, if like one of them is normal, then only the product will be a subgroup. But the case of ideal is even more even more complicated, because I mean, let me show you by this example that if we define ij to be this, then it is not going to be an ideal, because let me first give you an example, then you will understand what I am talking about. So, like maybe inside so maybe we can just take x to be fx or simply just rx, and I to be, let us say, the ideal generated by two things, 2x, and j to be 3x cube, something like this. Then we consider so 2x's, right, okay, 2x cube, of course this lies in ij, because it is a product of some element here from that, and then we can also talk about 3x square, or maybe I think here I can put 2 3, let us see. So 3x, okay, so 3x, just a minute, maybe the previous one was better, yeah. So 2x cube plus 3x square. So this is also, since ij is an ideal, so this also has to be in the ideal ij, but it is easy to see that this is not of the form AB, where A is in I and B is in J. Okay. So what I mean by this, if we define their product just by this, then that is not going to work, because I mean sum of two elements of this form may not be an element of this form. So therefore this may not be an ideal in general. So the whole point is, we cannot define, in general we cannot define the product to be this. For that we should consider some necessary modifications. So what is the natural modification that will do the job? Is simply we should allow all such finite combinations. That is exactly the definition of ij. Maybe I should erase this. This is exactly the definition of ij. So what is the definition of ij? So it is of the form a1 b1 plus a2 b2 an bn, where each ai is from I, bi is from j, and n is a natural number. Okay. So we should consider not only products of this type, also any finite sum of such objects. So now it is easy to see that this is going to be an ideal. You can immediately check. An ideal of R. So since we have thus defined, okay, before I extend this definition for any finite collection, let me talk about some examples, then that will just doing that, if you do that, you will make sure that you have indeed understood. So let me give a few examples, come exercises. So just take R to be z modulo z root minus 5, take I to be the principal ideal generated by 1 and j to be the principal ideal generated by, and then you compute what this I times j is. Similarly, you can do the same. So here you take I to be, so these are just kind of easy exercises. By doing, you will ensure that you have understood the definition. So here I is, let us take 1 plus I root 2, the principal generated by this, here 1 minus I root 2, and then as usual you can talk, you can just simply find what ij is. Okay. Here you can immediately see that it is going to be the ideal generated by 6. Okay. Or more generally, you can do you can formulate and ask the you can formulate and ask the analogous question for any general z root d. That is, you can take some, let us say, a plus b root t, the principal generated by that, and then then a minus b root d, and thus you can then ask that what is the product of these two principal ideals. Okay. So, I am leaving the computations to you. Now, So, now let us extend this definition of product for any general collection. So, let I1, In ideals, these are ideals of R. Then we want to define I1, I2, In. So, how we should do is, we should consider all finite sums of products. So, basically we should the way we should define is the following, that is let us say A11, just like we have to somehow use different indexes. Okay. And then again another product of this type, A1, A22, AN2, and thus you continue A1M, A2M, ANM, with, of course, I should tell you that each A11 up to A1M that lies in I1. Similarly, A21, A2M lies in I2, and similarly the like if I take the last from each and every summand here, AN1, ANM, N. Okay. So, that is how we define the collection of define the product of any finite collection of ideals. Okay. And the following observations I am leaving to you as an exercise. So, like addition of ideals, the multiplication of ideals is also associative. That is, if for given ideals A, B and C, A, B, C is same as A into B, C, and once we have defined the product for any finite collection, so here in fact it is exactly same as A, B, C. Okay. So, the properties for addition and multiplication, these are defined. Now, we should now go for the distributive properties. So, distributivity, so the statement is exactly, this is obvious one. Suppose we are given, okay, let me write it, A1, A2, AN are ideals, and another ideals, let us say B, all are ideals of R. Then of course, first we can take the sum of AIs, then getting it multiplied by B, and that should be same as, okay, and as vice versa. So, the similar statement would hold if I consider B to be on the right side. So, remember that if the general ring is not commutative, then there is no reason that Ij will be same as Ji. There is no reason for that. Okay. If it is commutative, then we are done. Okay. So, since we have not assumed commutativity in general, so we do have another statement of distributivity where B is put on the right side. So, I am leaving that to you because it is obvious. And then, so as I said, the product of ideals is slightly like it is it's somewhat it's not as easy as sum of ideals, because given any finite collection, its sum is the smallest ideal containing each of these summands, right. So, this is so again let me repeat that, given any collection of ideals I 1 up to I n. So, what is the smallest ideal containing all the ij's? So, it is exactly this. Okay. However, for this it is rather the thing that the way ideal is defined. So, this product you see this ideal is contained inside I 1, because it is basically if you take any typical element here. So, it is an element from I 1. Okay. So, just a minute. Okay. What I should do is I should make a small amendment that if the given ring is commutative, then since like in each of these terms, if you see the term is just a multiple of a1, a multiple of an element of I 1, since the ring is commutative. So, each of these terms will be inside I 1. So, therefore, this is going to be a ideal contained inside I 1, right. There is nothing wholly about 1. So, basically this is going to be thus contained inside the intersection of all ij's, okay, provided provided the ring is commutative. So, let me put it as a remark here. Let me put it as a remark here. So, first of all, of course, the following holds in the generality, that is intersection okay. So, suppose we are given a collection of ideals, an arbitrary collection of ideals, of R, then the intersection is going to be an ideal, okay, ideal in R. It is easy to verify, and now come to this case. Assume R is commutative, assume R commutative, then the product is actually this product ideal is actually a smaller ideal, okay. This is easy to see, okay. So, now so therefore, whenever there is intersection, then the natural question to ask is what about union, what happens for union of ideals. So, like subgroups, you can immediately say that because ideals are first of all additive subgroups. So, the union of two ideals is not going to be an ideal, it will be an ideal if and only if one is contained in the another. So, it is exactly same like subspaces or subgroups, but however, like so if one is contained in the another, then its union being the top one is going to be an ideal, and the basically the analogous thing that holds for any such infinite increasing collection as well. So, let me do it, let me talk about that. So, what we have just seen, that if we are given an increasing, we are given like two ideals I and j, I is contained inside j, then j being the union of I and j will be ideal. So, this actually holds in the generality as well. So, suppose that we are given, so this is called increasing union, called the increasing union. What it is, that suppose we are given a countable collection of ideals, of R, and with the condition that I 1 is contained inside I 2 and so on, then we can consider the union. It is easy to see that this is also an ideal. Note that this union may not be attained by any IN, it need not be attained by any IN. So, although this may not be inside this collection, however, still it is going to be an ideal. That is easy to verify. So, increasing union of ideals is again an ideal. Okay. So, thus it shows that like if we are, all this shows that if we are given, if we are given some ideals in inside a ring, then from that how to how to generate from any given collection of ideals, how to generate more ideals out of that. So, these are the usual operations, that is sum, product, intersection, and then for increasing collection we take the increasing union. Okay. All right. Now, let us move to some other examples of ideals. So, yeah, so the time is almost ending. So, let me quickly tell you what I am going to do. So, okay, so this is another example. So, let R be a commutative ring. I am now going to consider all elements which are nilpotent inside R. What do you mean by nilpotent? Some power will vanish. So, the collection is X in R such that there exists n, x to the power n is 0. You see the reason for calling the elements nilpotent, because the definition is pretty similar to that of nilpotent operators. So, let us consider in fact nilpotent operators, the nilpotent elements of you can immediately find out which ring I am talking about, the ring of all operator, endomorphism ring of the vector space. But anyway, so this is how a nilpotent element is defined in a general ring, and we consider its collection. The only difference here is that like here we are considering inside a commutator, inside a commutative ring, but given a vector space, it is all endomorphism ring, the ring of all endomorphism is going to be commutative. So, therefore, if we are given two nilpotent operators A and B, unless they commute, we cannot say that A plus B is going to be nilpotent. Okay, that also is the scenario is same for any general ring which is not commutative, but however, inside the commutative setup it is easy to see that I is an ideal. So, how to show that? If we are given two elements x and y, so let us say some x to the power some n1 is 0 and then y to the power n2 is 0, we consider the something far far ahead than both n and m, both n1 and n2. Then we want to show that the power also vanishes. So, like how should what is the most natural way to compute this? So, when the x and y are usual numbers and everything, we can expect, we do it using binomial theorem, but now they are from the rings. So, therefore, we also should expect some binomial version of binomial theorem in case of a general commutative ring. That is exactly the point, binomial theorem. So, if R is a commutative ring, then for any A, B in R and N in N, one has the following NCR a to the power n minus r, b to the power r, or from 0 to n. So, how does one prove it? The proof is the verbatim repetition of the proof of binomial theorem for real numbers or complex numbers, because how do you prove it? You prove it by induction, and there the crucial step was something called some identity called Pascal's identity on binomial coefficients, but that identity must this is a identity on just binomial coefficients. So, therefore, that identity is we can apply that whenever necessary, that identity does not have anything to do with the ring. So therefore, in general commutative ring you also establish binomial theorem, and with the help of that here you can immediately by breaking it into the by splitting it into the terms, you can immediately show that this is 0. So given any commutative ring, the set of all, the collection of all nilpotent elements is going to be again a nilpotent. It's going to be an ideal. Okay, so I just now finish with one more thing which I just forgot to mention. That is, in case of rings of continuous functions, we see that if we fix a subset S of x, then all functions vanishing to that is also going to be an ideal of the ring of continuous functions. So now what we are going to talk about is exactly similar, but things are slightly different. So like let's take any fn, or like if you want let's take any field f and f to the power n and consider any S non-empty subset, of course, because for empty set things would be some extreme one. Anyway, so now we consider we consider all functions, polynomial functions. Okay. So earlier it was all continuous functions, but now I am considering only polynomials such that Fs is equal to 0 for all S in S. Okay. Just to see the difference, earlier we had a topology, here we do not have, earlier we did metric or topology, but here we do not have that. So therefore here it is not sensible to talk about continuous functions, but however we do talk about polynomial maps. So like here we can safely consider all the polynomial maps, all the polynomials that vanishes at every point of, so given any polynomial f, we can regard that naturally as a map from fn to f, okay, just by substituting. So yeah, sending each f to, okay, so taking any alpha n, we send it to, we evaluate the polynomial at the point alpha up to alpha n. We will talk about this evaluation in details very soon, but right now it is clear what I mean. So if at every point, yeah, so we consider all the polynomials which vanishes at every point of S, it is easy to see that this is an ideal of okay. So here like you see that the setup is almost like similar to that of what we have done for continuous rings of functions. So this is called the ideal of the set S. Okay, this is also an ideal. Okay, so enough examples of ideals we have seen for the time being. So in the next lecture I will talk about the main point of considering ideals, namely quotients. So yeah, so in the next we will talk about quotient rings, and like as I keep saying that ideals are the analogues of normal subgroups here. So normal subgroups and homomorphisms are intimately connected. So therefore in case of groups we have already seen, we are going to see all their analogues in the set of rings in the next lecture. Okay, so with that I will finish this lecture.